Now that you've seen the ALU operations and how to set the condition codes, let's look at the instructions that actually use those condition codes. The ones you might be most familiar with are the jump instructions, which allow you to implement control flow. The whole family of jump instructions will have opcode of 7, but will have different values in the function field. For example, if the function is a 0, that says that we're going to take an unconditional jump, and no matter what the opcodes are, we're going to take the next instruction from whatever address appears in the destination field. In contrast, for all the other functions, the instructions are going to look at the condition codes and decide whether to take the jump or not. And you'll have jumps corresponding to all the standard conditions. So LE is less than or equal to, L is less than, E is equal, NE is not equal, G is greater, and GE is greater than or equal to. So let's look at the condition codes, and then I'm going to come back to this slide and talk a little bit about the encoding and all the other things that we've looked at. So recall that there are 3 flags. Only 2 of them are used in the jump instructions, the 0 flag and the sign flag. And so the way the conditional jumps work is that whatever the last ALU instruction left in the condition codes, we're going to use that to decide whether we should jump. So if you want to jump when that last thing was greater than, what that means is that the 0 flag had better not be set, so it needs to be 0. And the sign flag had better not be set, so that needs to be 0. So if those 2 conditions are true, then the previous ALU operation resulted in a greater than, and therefore we would take the jump. Let's take another one, less than or equal to. So that says that the previous instruction either generated a 0 for equal to or set the sign bit. So in this case, either of those bits could be set. So you can go through this table. I'm not going to do that in the video. You should do that on your own and make sure you understand how the condition codes map to the conditional jumps. Let's go back to the previous slide and look at the format of the instruction. So the jump instruction is pretty simple. All it takes is the kind of jump instruction, so jump or JLE, and then an address. And you can specify that address as a hex number. You can specify it as a label using the labels with the colons in your code. And the meaning of this instruction is simply that the destination value that's in this field is going to be placed in the PC, and that will be the next instruction that you're going to execute. So let's look at this in practice. Here's a program, and I'm going to pull it up in the simulator so we won't spend a lot of time looking at this slide. It's going to go through a number of comparisons and demonstrate how to use the jump instruction. So let us turn to the simulator. And I have to find the right window to share. Okay, so here is our simulator. So let's turn to the simulator. I've already loaded the program. Our registers are all 0, and we can see our condition codes down here. So what we'll do is first, we're just going to set 2 constant values into the registers RSI and RDI. So let's initialize those registers. So RSI is FF and RDI is 1. So in this first example, I'm going to say if RSI is bigger than RDI, I would like to return 1, otherwise I'll return 0. And when I say return, I'm going to put it in the register RAX. And why I'm using these registers will become clear in just a few videos. So what I'll do is I'll initialize RAX to be 1. So I'm going to assume that I'm going to return a 1 here. And if RSI is not larger than RDI, then I'm going to have to change it to a 0. So you can do this in either direction. Let's run one more cycle. So now we've initialized RAX to 1. Because I don't want to destroy the value that's in RSI, I'm going to make a copy of it by moving it into R10. So if we do one more cycle, we'll now see that both R10 and RSA contain FF. So in this case, we do expect RSI to be bigger than RDI because FF is bigger than 1. So now we're going to set the condition codes. The way we'll do that is we'll say, okay, I'd like to subtract RDI from RSI, which is now in R10. So when I do that, we do the subtraction. R10 goes to FE, but more importantly, when we subtracted 1 from FF, we should not have gotten a negative number. And if we look at these condition codes, they're not set. So now what we say is, okay, if RDI was greater, then nothing should be set. And so I want to say jump on greater to my next label, because if I don't jump, what I'm going to do is I'm going to place a 0 into RAX and say, actually, it wasn't greater. So in this case, I initialized it, assuming that the condition was true. And if the condition was true, then I jumped to my next label. Otherwise, I set the value to be 0. Let's look at another example. This time, I'm going to ask if they're equal. And if they're equal, then I want to return 1, else I'll return 0. So we should expect a 0 this time. So once again, I'm going to initialize RAX to be 1. So let's continue along. Actually, I need to execute those instructions. Great. And now, once again, I'm going to copy RSI into R10. And then I'm going to do the subtraction, so I set the condition codes. And you remember, the condition codes aren't set. But this time, my branch condition says jump on equal. Well, jump on equal is only going to take effect if the Z bit is set. That is, if the last 2 operations produced a 0 because they were equal. Since they didn't, we should expect that we're not going to take the jump. And therefore, we're going to execute the next instruction here at line 30 and put a 0 into RAX. So because the values weren't the same, we returned the 0. One more example. Let's initialize RAX to 1 again. And this time we're going to do an AND Q of R10 into R10. Recall that what AND Q does is it preserves the value in the register, so it's not going to change it, but it sets the condition codes. So we do that instruction. The condition codes are not set because FE is greater than 0. It's not equal to 0. So neither the sign bit nor the Z bit are set. And now I'm going to say jump on greater than or equal to done, because the condition I'm testing here is RSI greater than or equal to 0. And so because greater than is true, i.e. we were greater than 0, we're going to take the jump and we're going to leave the 1 in RAX. So I encourage you, you can play with these examples, write your own, but get some practice mapping between traditional control structures that you're used to in a higher level language and how you would implement them in y86. Now it turns out there's another conditional instruction that we alluded to much earlier that now you should be able to understand. So let's switch back to the slides for a moment and go on to the next slide. And it turns out there's a conditional move instruction. So you may recall when I introduced the register to register move, I said, for now, we're going to leave the function to be 0. But it turns out that all those functions that you can use with the jump instruction, you can also use with the register to register move instruction, and we call it a conditional move. And what it does is it says, only move into this register if the condition is true. And so that's a different way that we can implement essentially control flow. So on the left-hand side here is an example very similar to what I just showed you, which is that we initialize values into registers, and then we are going to make a copy of the register into R10, and then I'm going to do the subtraction just like I've done, and based on the result of the subtraction, I'm going to do a jump. But the whole reason that I did that sequence is I wanted to decide what to put into RAX. So there's another way we could do that. So what I'm going to do now is I'm going to initialize RAX to 0. Notice that I'm initializing it to false here. The condition is not true. because I'm going to use that conditional move instruction to say, well, if it were true, then I'll do this move. And the value that I want to move is a 1. So RAX is still going to be either 0 or 1. But this time I'm initializing it to 0. Now I say, let's set R11 to be this 1. Once again, I'll create the temporary value for RSI. I'll do my subtraction. And now what I'm going to say is conditionally, on whatever condition I want, so I can do any of the conditions I did before, move R11 into RAX. And what that tells us is if the condition I'm interested in was true, then take this value in R11, the 1, and move it into RAX. So let's just go through that in the simulator quickly. We'll pull that up and we'll go to this program. So this is the same program essentially, but it's using the conditional move instructions. So this time what we're going to do is we're going to initialize RSI to FF. We'll initialize RDI to 1. And now I'm going to put a 1 into register 11 because this is going to be the value that I'm going to conditionally move. So when I want to test if RSI is bigger than RDI, I'm going to start by initializing RAX to 0. I'm going to make a temporary copy of RSI just like I did before. I'm going to do the subtraction just like I did before. And now what I'm going to say is if in fact RSI was bigger than RDI, so a conditional move greater than, I would like to move a 1 into RAX. And in this case, we know that that's true. So when we move, we get the 1 in RAX. The next examples work exactly the same. So we initialize RAX to 0, we save a copy of RSI, we do the subtraction, and then we use this conditional move instruction that says, if in fact the previous instruction produced 0, the Z bit was set, then I'm going to move the 1. Well, the Z bit isn't set, so I go 1 cycle, I don't change the value of RAX, I return a 0. Last example, exactly the same. We initialize, we copy, we do the and now this time when we get to the greater than or equal to instruction, it's true, and so we should see that 1 conditionally move into RAX. And we do. So I hope by now you've gotten a sense of how the condition codes interact with these conditional instructions and let you implement control flow in your y86 program.